For 380 million years since plants first appeared on our planet, they've been changing. But they change slowly, at least in human terms, very, very slowly. We have a challenge in the changes that we as humans are creating in our planet at the moment and the impact of those changes on plants. Consider this, we're a plant-based species. We rely on plants for food, we rely on plants to clean our water, and we rely on plants to clean our air and provide the oxygen that we breathe. We as human beings are creating in our environment is impacting negatively and severely on the ability of plants to yield what we need them to yield, to adapt to the changes that we're making in the environment, and to withstand predation by insects and pests and disease because of the stress we put those plants under. We have a problem. The bases of that problem are two. One, an increase in population, which for the last 50 or 60 years has grown inexorably. At the same time, agricultural technology for that 60 years has enabled us to increase productivity more or less in line with population to feed the people that we have on the planet with us. However, for the first time in that 60 years, the stresses we're creating in our environment are now starting to have an impact on yield, on productivity, and a gap is forming between population increase and yield decrease. And it's this gap that's forming a tipping point. We need to stop degrading the performance of our planet and start enhancing the performance of our plants fast. We need to be able to quickly develop new plant species which yield more quickly, yield under a wide range of stress conditions, and which resist the diseases which prey on them when they are diseased. We need to enhance the performance of plants naturally and quickly. For more than 140 years, one very promising route to enhance performance for plants has been polyploidy, or natural gene duplication. Polyploidy has been pursued as a strategy for more than 80 years and not very successfully. But 20 years ago, our chief scientist Malcolm Lamont, taking a novel epigenetic approach, cracked the genetic code. And we've now refined Malcolm's epigenetic approach into a highly reliable and efficient method for creating new high-performance varieties of any plant species. As for epigenetics, let me show you what I mean. Epigenetics is the science of how organisms respond to stress at their genomic level. And by subjecting plants to specific stressors, well, at base, the plant will either adapt or die. And we've developed the ability to cause them to adapt and to produce new, higher performing varieties to meet a wide range of needs. And those new varieties can be naturally bred into millions and billions of new plants to provide higher yielding forests and plantations throughout the world. As for our disease resistance and stress tolerance capabilities, those same epigenetic processes give us the tools to reverse the losses we suffer from climate change, from land and water degradation, and from tough chemically hardened bugs. At the same time, they answer the cry for affordable renewable energy, efficient carbon capture, and reliable food supply into the future. And so, much of what I wanted to share with you here today can be reduced to 8 simple points. Firstly, the plants we produce are natural. They're not genetically modified organisms or GMOs, and so are not subject to the safety constraints applied to those artificial species. Secondly, they're fertile and deliberately so. Thirdly, the performance traits we induce in those plants are heritable, so they carry on down through the generations and also down through time. Fourthly, our plants are uniquely identifiable. They have a singular genetic fingerprint. Never existed before, won't exist again. So we can identify them of all the species that now exist or have existed. So bringing that all together, fifthly, our plants are detectable remotely from satellite data. And that makes it possible for us to provide our licensees with real-time performance data in relation to our plants, and also obviously to enforce our rights and their obligations in relation to their licensed use of those plants. And sixth point, our plants are protectable under patent, plant varietal rights and a range of other conventions. Of critical importance to our commercial users, of course, is the fact that the seventh point, our plants deliver them a unique, in fact, an almost unfair competitive advantage. Because they enjoy much higher yields for not much increase in cost, they have a larger margin to compete in a highly competitive marketplace. And lastly, of interest to all of us, is the fact that our plants, the technology for our plants, is applicable universally across all species, including those we've developed for food. Right now we're standing in the PolyGenomX test grounds, and I want to share something very, very interesting with you. This is a Paulownia, one of the naturally fastest growing plants on the planet. This plant is 16 months old and has done a fairly credible job of putting on size in that short time. Now let me show you something really special. And now let's have a look at the polygenomic variety of exactly the same plant. Same age, same location, same genetics, but a far more carbon efficient plant. It takes more carbon from the atmosphere and packs it into plant material. Look at the girth of this plant. It's grown so fast it's even picked up the name tag and carried it up the trunk as it's grown. And significantly better and greater height compared to its standard. And this is a great illustration of the first performance characteristic that we induce in polygenomics plants, that of faster growth, earlier maturation, high yields. The second performance trait we induce is that of environmental stress tolerance. And the third trait is that of disease resistance. The latter two cut losses. The first one increases yields. Combine those in polygenomics plants delivers the possibility, the advantage, the performance advantage we're going to need to survive, to resource ourselves into the future. We call it the polygenomics factor. So when you have that PGX factor, the ability to create new plant intellectual property almost at will, how do you commercialise that? Well, there are a couple of very straightforward answers. Firstly, you can find an already profitable, large-scale plant-based enterprise using the species you've enhanced and license them to use the new species. They gain immediate increases in productivity for no changes in procedures or equipment or training. It's an immediate through to the bottom line gain for them. They're excellent licensees. And we can do that for crops such as tomato or jatropha, biofuel feedstock, or wood pulp trees. Or we can take a very high value and strategic commodity crop such as rice and put that into an entity, a company formed for the purpose of owning that intellectual property, and then inviting investors to come into that to commercialise, to market that new plant species to the world in competition with the less efficient species that are out there now. And that company earns revenue from the royalties, it pays dividends to its investors, and PGX is one of those investors. And at the same time, the equity in that entity rises in value as the market share rises as well. So that's a win-win. We may do that for several species such as rice or coffee or cocoa or tomatoes, etc. But there may come a point where someone says, well, why don't you float that? Why don't you put that in the marketplace as a public company and make an initial public offering, which we can do. So we then sell off part of the equity that we have in the company we formed to carry that species. There are multiple commercialisation opportunities for polygenomics plants and for polygenomics.